number
12.
12. And then we got,
Oh, I get what you're saying.
so how big is this guy here?
2 by 3.
Yeah, this is a 2 by 3, and this is a
3 by 2.
3 by 2.
So they can be multiplied.
Yeah, what's kind of neat about this is if I turn it around, would it work the other way?
Yes.
Yes, because then the 2's would match, right? But right now the 3's match. That's what tells me I can do it. So in a sense I'm always disappointed because then that's more work for me. But the inner ones match, so I can actually multiply this. And how big is the answer going to be?
2 by 2.
It's going to be a 2 by 2. That's kind of nice. So we're kind of condensing all this stuff a bit.
Yep.
So I know I'm going to have a 2 by 2. Don't need that much room for that guy. So then I go 2 plus 3. So far is 5. Minus 4
Is 1.
is 1. It's crazy. Is that cool? Do you
Yeah.
guys see that? So to get the first row, first column, I do the first row times the first column. If I do this row times this, I'm going to get the second row, first column answer. So you get 6 plus 9 is 15. Minus 8. 7.
I didn't know what you were drawing. It looked weird.
Well, I was waiting for you to, you know what I was drawing. I was waiting for you to give me the answer. It's too easy, Jeff. So then we get negative 12 plus 18.
6.
What's the matter? I just wanted to do that. I'm doing in a counterclockwise motion on it. So negative 12 plus 18. 6 plus 0.
6.
And now I can do the first row, second column. I get negative 4 plus 6 is 2. Good. Alright, so multiplying matrices. Once you see how it's done, and I don't know, it's a little weird why they had to define it that way, but once you define multiplication this way, there's so much more you can do with these matrices.
Are we going to learn about that today?
We're going to learn about inverses today. And then we're going to learn a little bit something else too. This is my hope, as always. Alright? Yeah.
10-2, number 40.
Oh yeah, okay. Those gas prices are actually make sense again. Gas price problems in books are always a little scary. You're like, oh yeah, I remember when it was that much. It's actually, it's back to that much now. This is back on page 648, number 40. And it says, gas station has 3 types of gas. Regular for $3 a gallon. Performance Plus for $3.20. And premium for who's it what? $3.30. On a particular day, 6,500 gallons of gas were sold for a total of $20,050. Blah, 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 blah. So right there in that one statement, there's 2 equations. Right? What are my unknown things in this problem?
X, Y.
True, that's what the variables are, but what are my unknowns?
So, how much regular?
Yeah, how much of each type? Right, how much of this type do they sell? So let's say they sold X of regular, Y of power, whatever the hell that was, and Z of premium. As I lose my voice, you're like, come on, you could do it, Jeff, lose your voice. So, in that one statement, they have 2 equations. On a particular day, 6,500 gallons of gas were sold. Okay, that's the easiest equation.
Yeah.
There almost always is a total equation. So what's the first equation I can write?
X plus Y plus Z equals 6,700. Or whatever the number was.
Yeah, whatever it was, 6,500. So always look for that kind of equation. It happens a lot, right? And then the second one is dealing with the money. So it says, they say that they made $20,050. So of course from the regular they made
$3.
$3 per.
So 3x.
So 3x, and so forth. What is it, 20,050? And then they just give you straight up 3 times as many gallons of regular as premium were sold. So which one were there more sold of? 3 times as many regular as premium. There's more regular, right? So when people write this, that gets me concerned. You're just being a little too literal, just trying to translate directly. But 3 times as much regular as premium. So it should be
Z3.
Yeah.
Or 3Z.
Whatever your preference. All right, and then you can go to town. The nice thing, that last equation is kind of useful. The last equation is stupid useful, right? Normally we take 2 and we kill a variable, right? We're not in the the next section is matrices. So you're not allowed to use a matrix on this. But normally we take 2 equations, we kill a variable, we take 2 more, we kill a variable. Now we can be a little more subversive about it. We can be a little more sneaky. I'm not going to kill the x.
You're going to change it.
I'm going to replace it. Yeah, exactly. So I can replace both of those with z's, combine my z's, and then I got 2 equations with just y and z in them. You guys see that? So again, there's a lot of ways. The normal way to do it is to kill something twice. But depending on what you know, there's other ways to do that same thing, to kill or get rid of a letter between 2. Here I can just do it a lot more directly. Is that cool? Is that as much as I'm doing? All right. Okay, not too bad. Anything else from homework? All right, cool. All right. I can live with that. Last time we made it up through 10.4. I think we made it through 10.4, if I'm not mistaken. Yeah. Because the last part is matrix multiplication. Make sure I didn't skip anybody. Nope. Okay. All right. So it's like that first guy. In fact, here, let me give you a freaky dude. Start us off here. Multiply these 2 matrices here. What's that? Isn't that neat? They're not inverse. It's not an inverse situation, right? If they were inverses, the multiplication should come out to be 1, exactly. Because then it would be a multiplicative identity at the end. When you multiply these, you actually get the 0 matrix, right? Now, in regular numbers, that doesn't ever work. You can't have 2 numbers, neither of which are 0, that multiply by 0. That's freaking possible, right? But of course, matrix multiplication is defined so weird. You expect weird things like this to happen. We call this, these are 0 divisors. Believe it or not, is the name given to them. Because somehow they divide into 0 and come out with an actual answer, right? That's not 0. It's kind of weird. Now, there is no true matrix division. So I've always hated that name because it makes you sound like there is division. No, there isn't. But oh well, that's the name they gave it. There's nothing special about this to know. I just want to show you this weird example. This is the one I was trying to create last time. I just kept coming back to the identity. So what we want to focus on today is how to find inverses. And let me first ask you, if I was back in 1D, sort of 1D, one dimension in a way, if I had a function like this, how would I find the inverse function? Yeah, switch the x and y, and then resolve for y, right? I'm going to come back to this, so I'm going to put this little dude up here. We're going to do this right now real quick, and then I want to show you how matrices do the same kind of thing. It's kind of cool. So I have this, I want you to realize I have this function of x and it equals y. And then what I really want to do is turn that bad boy around. Now, I like that. So the first thing you do is switch the x and the y's. I'm going to just kind of do this quickly, because I want to make a point of this later. It's really kind of a cool, well, we'll see. We'll see if you guys see what's happening. So this, for some reason, it gives people a lot of trouble. I'm trying to solve for y, right?
Yeah.
Now, obviously, this guy's a problem. So I should know right off the bat I got to multiply that guy up there. And then here's my it's not a y, it's an s. Yeah. Here's my y stuff. So whenever I'm trying to solve for something that's more than one variable I'm trying to solve for, what do?
Two on the same side.
Get them both on one side, so they got to drag them out. There's not really two y's up there. There's only one. That's where I know somebody's out there going, yeah, this guy's crazy. But there's not two y's up here. There's just one. I just don't know that yet. So if I subtract that y over and add the 5x over, take the y out, and then I got this. Funkadelic. All right. Now, real quick, go with me here for a second. What's the horizontal asymptote of this guy? We're getting close to the final. It's going to be on the final. What's the horizontal asymptote for this guy? Yeah, it's in the same degree, so it's 1/2. So that's where the outputs have to go to 0. So, in fact, that's what the outputs have to approach when x gets really, really big. Now notice on this guy, what's the vertical asymptote?
There's
1/2, yeah. So that's just the switching of the x and y, the inverses of each other. So that's what x cannot do, and this is what y cannot do. Y can't go to 1/2. Right? So that's why I end up getting the same answers there. I can do the same thing with the y-intercept and the x-intercept. Of course, everything just switches. All the x and y stuff just switch. But later, I'm going to come back to this. So this is, let's say this is f inverse. We're going to refer back to that later. But the reason I want to bring this up is because that's how we find inverses. And what we have now, let's go to a 3x3. 2x2 is almost too easy. I want to get the general approach, and then the 2x2 has its own special quick way to do it. 2x2 is too easy. So if I have, what I'm trying to do is figure out, let me do it like this. If I have a matrix times some like x, y, z, we've seen this kind of thing before, so this is a 3x3 situation. I want to figure out the inverse so I can apply it to both sides. We did that last time. We didn't find the matrix, so I just gave it to you. And then we solved this equation like this. So what I want to do is, I want to take this matrix, and this is like x, y, z. And this is like, I'll call it x1, y1, z1. So I want to solve for x, y, z, and I want to get that equal to something times x1, y1, z1. It's really the same thing I'm trying to do here. Instead of having something happening to x, I want to, and of course I switch the x and y, I want to turn it around so I can see, I can make something happen to this side instead. So that's really what I'm trying to do. So let's see, if I had, let me do one that I know is going to work. Yeah. Here. So I want to say, let's say that this is, this is of course what's happening with x, y, z, what's happening with x, y, z, what's happening with x, y, z. But I want, in each case, I want to equal it to x1, y1, and z1. And then I want to do basically what we did here, which is to undo everything that's happening. So I'm going to actually set it equal to this, the identity. So what's really neat is I call this kind of like Memorex. So what I'm going to do is I'm going to row reduce this bad boy all the way down to the identity. which is equivalent to getting all this stuff out of there and getting x by itself. And in the process of doing that, everything's going to move to the other side, and it's going to be all the inverse operations. That's what finding an inverse does. It takes everything that's on this side and makes it on that side in the inverse. So if I row reduce this and do the same things with this, so I got this giant row here. Row 1 is the whole damn thing across. So let's try to do this. We're going to do this together. It's a good review of row reduction. What's a good first step? I'm just trying to row reduce this bad boy. So I want him to end up looking like this.
Multiply the top by 3 and then store it in
Cool, I like it. So 3 row 1 plus
row 3.
row 3, 2,
Row 3.
row 3. So I get 3, negative 6, negative 12, 3, 0, 0. So I just go all the way across. And I want you to realize, this is kind of like a blank tape. So it's going to record all of the opposite operations I'm doing. Every time I do something here, it's canceling something else out. So this is just keeping track of all those opposite operations. So at the end, it's going to be the complete set of all the operations that are the opposite of what this guy here was. That's exactly what I want that thing to do. I want it to be the inverse. I want to do the opposite stuff than the original one does. So what do you get here when you add those together? Crazy. Oop, let's put it down, row 3. 0, yes. 3. 3. 1. Cool. Yes. Now at the same time I can do what?
Negative 2, row 1, row 2.
Yeah, so now I can do negative 2 row 1 plus row 2. So I get negative 2, 4, 8, negative 2, 0, 0. Cool. So then what do you hear? You get 0, 1, 2, negative 2, 1, 0. And then the first guy, I leave him alone. Alright, let me stop there for a second. So I don't know if you remember last time I was trying to show you how you can break steps down into what I call I can't remember exactly what I called, the atoms or the DNA of operations. So if I had one little dude, one of the last things we talked about last time was if I had this guy, this is really just the first row plus the second row, put it into the first row. So I said when I operate on something else with this, it's going to make that same thing happen to this guy, right? So I started with this like 1, 0, 0, 1, just the triple, the 3x3 version of that. So every time I'm doing something the opposite operation, it's adjusting this guy in the same way. So he'll end up being, like I said earlier, a combination of all these little one-step opposite operations of what this guy was all about. That's why they end up being inverse matrices. Whatever I end up with here would kill this, would take it back to 1 if I applied it to him. Because he's got all the opposite stuff that this guy's got in him. That's why this process makes total sense. That's why I love this idea of memory. It's just memory. Let me remember all this opposite stuff you're doing, and then I got a giant matrix that's got all the opposite stuff that this guy had. So of course they're inverses of each other. They would undo each other. Which is what I want with this. I want to multiply both sides by a inverse. Bam! Kick ass. Now you might realize you can't always find an inverse for a matrix. So we'll talk a little bit about when you can't find an inverse. This one's going to have one. Let's see. What else can I do now? Keep you there.
Multiply row 2 by 2.
Let me see.
And then replace row 1.
Yeah, good. So row 2, twice row 2, plus row 1, so row 1. So here I get, so twice this guy, which is kind of nice. So I get 1, 0, 0. It's really nice. I need some more room for that. Say again? Sorry.
Nothing.
Let's see, negative 3, 2, 0. That's cool. The first one's done, right? And the last one, this is not pretty, but what can I do with this row? Yeah, divide by 3. So I get 0, 0, 1, 1, 0,
1/3.
1/3. And then the middle row, what can I do to kill that 2?
Multiply
Just
row-
have to,
row 3 by negative.
yeah, multiply row 3 by negative 2 to kill him. You all good? Going a little bit fast, but hopefully everybody's decently comfortable with this. What's up? Oh, what's up?
Well, with the mirror, the inverse part, what are we doing with that?
This is one giant row. So whatever the hell I'm doing with row 1, it's going to happen to the whole damn thing. That's all. Nothing special.
Okay.
So that's why I put next to everybody 3 times it. And then I just add row 1 to row 3. Or whatever it is I'm doing at the moment, right? I just do it through the whole damn row. Just like anytime it's augmented. We normally had it augmented with just something that was that big, right? But we'd still, to solve it, I would just still do the same thing to this. So now I just augmented it with a giant freaking 1. With a 3 by 3 that represents 1.
So using the example of the first one, 3 row 1.
Here?
When we first started, yeah.
Alright.
Okay, so 3 times row 1. How does that go with the 1, 0, 0 portion?
So right here, here's 3 times 1 is 3, 3 times negative 2 is things all the way across. And then when I add it to row 3, what's 3 plus 0? 3. Right, so every time I add these, 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 all the way across. Yeah. So it's nothing new. I'm just using it for a different purpose. Right? This process is the same process as before. Alright. So now things get just a little bit bad, but not horrible. So I know I've got to multiply this by negative 2, row 3, to kill that guy. This is my laser. So of course I'm going to finish here negative 2, 0, and of course this would be
Negative 2/3.
negative 2/3, kick ass. So then if I do that, again, the first row is the same. Second row becomes 0,
Negative 4.
negative 4,
1.
1,
2. Negative 2/3.
negative 2/3, and then I get 0, 0, 1. 1, 0, 1/3.
And so that stuff on the right is your inverse.
Yeah, so if the matrix I started with was A, this guy now is A inverse.
So it's just A inverse times, never mind.
So if I wanted to, if I had an equation that had these coefficients in it, right? If I had x, y, z with these coefficients, I could just multiply by this guy on both sides and get the answer. Right?
Okay.
So 2 things I want you to do. 1, verify the R inverses. And then 2, so how are you going to verify their inverses?
Multiply them together.
Yeah, if you multiply together, you're supposed to get 1,
1,
1, 1, 0, 0. Okay, good. So do that first. And then secondly, try to solve this. Right? It's coming back. I binge watched that thing, man. It was awesome.
I do too. I have to wait for it to come out.
My
now.
God.
Wait for the next season. HBO's stupid. They don't let you buy it right when it's finished.
Well, at least they are considering detaching themselves from cable. Yeah. I heard they're thinking about making them pay separate service for HBO. That's awesome.
That would be cool. I'd probably do
That's
that.
the way everything's going. Hopefully, cable's just going to kind of go away.
I don't
No, yeah.
I don't have cable either. It's all Netflix and Hulu and
Yeah.
see, I buy my
Exactly.
stuff.
Yeah.
It's cheaper.
If you really want to watch something, just buy it.
Yeah, I buy a show on it. You still need it though, because how else are you gonna have shows that you have to buy?
Hmm? Yeah, I got the really basic cable.
Yeah,
Yeah,
Gives me my-
first link to check.
yeah. I just use an antenna and then have internet.
Get a high definition antenna.
That's all it needs. You get local channels.
We actually have.
Like multiplying one over.
Yeah. So you take this A. So we got what they want from here.
No,
So what, yeah, how do we?
You
Hold on.
should, or else will you be doing this right now?
I wasn't doing it.
Okay, that explains.
Now I got it. I got what I need anyway.
All right. So now everybody got this here.
Yeah.
So let me write this. So 1. If I take this matrix here.
So you take the original and multiply
You erased
by
your
the
inverse.
Or
What did I erase?
You erased your inverse.
Yeah.
Oh, okay. Well, you guys are here for something.
So is that all we're doing?
Whoops.
Here's A. What's A inverse? What did we just figure
I
out?
don't know. You erased it before you finished writing it down.
Screw yeah, I gotta just take it out of here. Let's see. This is what we should have got. Hopefully, this is what we got.
Did it work? I believe you.
Alright. So we're just doing this to give you some more practice right now with matrix multiplication. You know what the answer should be?
1, 0, 0.
Yeah. 1, 1, 1 on the diagonal. So it's kind of a nice situation to be in. So I sure enough I get -3 plus 8 is 5 minus 4 is 1. So far that's looking good. Yay. So then I get 2 minus 2 plus 0 is 0. How are we doing so far?
Excellent.
This is exactly how I do it on the paper, and it just kind of help yourself out. You're not used to looking at things like this. So 0, 4/3, minus 4/3. Kick ass. And then you get -6 plus 12 is 6 minus 6 is 0. 4 minus 3 is 1, 0, so that's 1. 0 plus 2 minus 2 is 0. And then you get, let's see, 9 minus 24 is -15. Plus 15 is 0. -6 plus 6 is 0. 0, what do we get there? -4 plus 5 is 1. Kick ass. So if I ask you, find the inverse and then verify that they're inverses. Don't just circle your work. You got to actually show me, do this multiplication. And then this would really look like, here's what it would look like in its full glory. I really want you guys to understand what this means down here. So I'm trying to solve, that's that. Those are the same thing. Is that cool? If I took A and multiplied it by X, Y, Z, I'd end up with those 3 pieces to it. And they're equal to the components that are across from them. Right? Is that cool? So that represents the same thing as this. My A is my coefficients, my X are my variables, and this is the answer matrix there.
The XYZ part from originally when we started it with the Y equals AX, and then you had, I don't know. like unreal stuff. I'm guessing there's X, Y, Z, but
Okay, yeah. It was XYZ. Yeah. That's what this would mean. This is a matrix times another matrix. I know this is 3 by 3, so this to be true, to be actually able to be done, it has to be 3 by something. And we know it's a 3 by 1, it has my 3 variables in it. In order to be able to do this multiplication, A is 3 by 3, so whatever this is actually has to be a 3 by something matrix.
right.
So when I have this equation, it's understood that this is my variable matrix. This piece here is actually a matrix that has all my variables in it. So when I multiply A times this, all the coefficients just go into place.
So then why did you put the Y equals AX?
Because I was trying to make it, so we started with this guy here, right?
Right.
And then we worked it out and figured out the inverse. So we could do the same thing if I have a matrix times these variables equals these variables. I want to be able to solve and get X equals A inverse Y. So I can take this and I can solve to get X equals 5Y minus 1 over 2Y minus 1. If I didn't switch the X and the Y, if I didn't switch the X and the Y in this process, I'd solve for X and get some mess with Y. So here I've got a matrix times the X matrix. I want to solve it so I can get that guy by himself. I want to see, well, what is the inverse applied to the Y? I want to turn it around like I did up here. So here I've got Y is some mess to do with X. And when I want to find the inverse, I want to get X equals some mess to do with Y. I want to turn it around. Yeah.
So all we have to do to find X or X, Y, Z is multiplied by X inverse.
Exactly. So now I wanted to make sure you got this connection. Now writing this didn't help me a damn bit. I just want to make sure you understood that this equation represents that system of equations, right? But now I can look more directly at it like this. So how do I solve this for X?
Multiplied by X.
Multiply by A inverse. Yeah.
But
It's got to be on the same side, right? What's up?
Now, when we multiply it up there, wouldn't it have to be? You can flip those. Because we.
Yeah, exactly.
So you can
So it
still-
doesn't matter which order.
That order doesn't matter.
Doesn't matter.
It just matters down there.
Just, yeah, down here it matters what side of the matrix you're on. This is not this guy's inverse buddy.
Okay.
Right? That's a good point. It doesn't matter which way I do this. It's going to come out to be this. Cool. So there it cancels. So I get X equals, and now I just have to multiply my A inverse. I just got to multiply that by negative 2, 0, 3. So I want you. So originally this is this matrix takes this and converts it to this. That's one way to look at it. It operates on this and it makes it become this. So what I'm doing is to say if I can collect all the opposite things that this is all about, I can apply those opposite things to this guy and it can convert it back to what it was to begin with. Very convoluted terminology way to say exactly how we solve any damn equation, right? We just do the opposite to both sides.
Where did you get the negative 203?
From the question. Yeah. Didn't come out of, like if I'm the student, it didn't come out of my brain. It's just they said solve this equation. So that's what they would say in the homework. They would say use the inverse to solve this equation. So they have to give it to you. So what do you get when you multiply that out?
You get 6.
And how? Let's double check things real quick. This is 3 by 3. This is
3 by 1.
3 by 1. So I know the answer is going to be,
3 by 1.
thank God, because I only have 3 parts in it that I care about, the X, Y, Z. I just want to know what those values are, right? So I'm going to get 6, let's see, 8, 0, minus 2, right? 8, 0, minus 2. Oh yeah, we're headed towards something. Negative 2, 0, 1. Oh good. Negative 1. Boy, that would have been interesting. You guys would have had a field day with that. Evidence that my teacher is a demon. I'm off by just a little bit. But I am a math teacher, so I am part demon. This is true. Thank you. Does that process,
That sucks. I don't like doing that.
does that process make sense?
No.
Just more, hold on.
The process itself is not different from what we were doing before.
No.
We're just using that process for a very interesting purpose. I set it equal to 1,
Yeah.
and then I row reduce. And that 1 really is a memory bank. It just keeps all those opposite operations are there in memory.
Yeah.
So whatever I end up with here, here's my original matrix, whatever I end up with here at the end has all the opposite stuff that my original matrix had. So it's going to be the inverse of my original matrix. That process is beautiful. It won't work in certain situations. So let's talk about 2x2s first. They're a little bit easier to talk about with things that don't work. So let's do this. Well, let me let you guys attack a 2x2 problem because they're relatively simple. And then I'll show you the shortcut. So I want you to use the same process we used to figure out A inverse here. I want you to use it on this little 2x2. Let's call it B. Well, that's gross, Jeff. It's not going to do this.
It's not.
What was that?
Yes.
So is that what X equals then, the 6, 6, 9, 1 second?
Cool. So X again is this matrix X, Y, Z. So X equals 6, Y equals 6, Z equals -4. So you guys might realize this is exactly what we do when we have just not a 3x3, but we just put this at the end of our matrix and we row reduce it. I'll talk a little bit more about that in a second. Hopefully you guys see I did this on purpose. Do you have a 1 here? No. But there's a very simple way to make 1, right? So the first thing I would do is add those together. Row 1 plus row 2 and put the answer in row 1. That would make a 1 there, wouldn't it? So the first thing I would do is row 1 plus row 2 to row 1. Get a 1 there. Or some of you guys might have gone ahead and just killed this dude. That works beautifully too. Still 2x2, doesn't matter what order you do it in, really. But if you do this first, you'll get 1, 1. You'll get 1, 1. All the way across. Okay. Is that cool? Just take these and just add them and put the answer up there at the top. So if you're doing it together, we just keep going that way. We'll see if we get to the same place at the end. Here, of course, I would say 3 times this plus this. 3 minus 3 is 0. 3 minus 1 is 2. 3 plus 0 is 3. 3 plus 1 is 4. And then what I would do is I would actually double this and multiply this by -1. Doesn't matter, there's a lot of different ways to do this. This is just the way I would do it. So you'd end up with 2, 0, -1, -2. 0, 2, 3, 4. And what's the last step here?
Like a 1.
Divide both of those by 2, right? So I'd end up with 1, 0, -1 half, -1, 0, 1, 3 halves, 2. So basically everything in there got divided by 2, right? And let me see, if I could do one thing here, what do I not need? I still want you there. Need anything else here? So if I take this, so A was 4, I'm sorry, B was 4, 2, -3, -1. B inverse is -1 half, -1, 3 halves, 2. Now somebody help me out. If I take a 1 half out, just make this thing look a little bit better.
1, 2, 3,
Yeah, -1, -2, 3, 4. Now look at this. Look at the relationship here. What happened with the 4 and the -1? They switched. And what happened with these guys? They just changed signs. So and that actually works every single time. If I start with A, B, C, D, and I go through this process, which we will not, what you end up getting is something interesting. You end up getting so in here you end up with, like we did here, they just switch places,
D, -B.
and these guys just become the negative. And what you end up dividing by is A times D minus B times C. And let's look here. What is A times D? -4 minus B times C minus -6. So in this problem, what would A, D minus B, C be? It would be -4 minus -6. I'll get 2, and that's exactly what everything was divided by. So that's the shortcut for finding inverses for 2 by 2 matrices, is this. So if I had a matrix, for example, and again, Chris, there's a lot of work we skipped. We're just gonna stand on the shoulders of people that did this. If I actually did this work, sort of like proving quadratic equation is true, right? If I actually did this work, I would end up with this as my answer. That is going to be my inverse. So this is A. This whole thing is A inverse. So that's pointing out how that is exactly what we got for that problem there. So that's kind of cool. So, for example, if I had this matrix that I'm just going to take out of nowhere here. First off, what would, so I know the answer is going to be this. All right, these switch and these change signs. And the way I remember this, because you do have to remember, is that the BC is negative in this little equation down here. So now that's the ones that become negative, and these must be the ones that switch. So what would the answer be? If this was A, what would A inverse be? What's AD? 5 minus -2. So 5 plus 2 is 7.
Times 5.
So given this A, how to find A inverse, I told you for a 2 by 2, here it is. Here's the process for finding an inverse. I said to identify what A, B, C, D are. Yeah, so now this is just, these two are going to switch. 5 and 1 switch.
-2 and 1.
And that becomes -2 and that becomes +1. It almost came out. It's supposed to come right out. Yeah, you should get the same coefficients as this guy.
You missed a negative 5 on that converse.
Oh, is it a negative 5?
Yeah.
Okay. Thank you. So then if I take that negative downstairs, right, this is what we got for the inverse earlier. If I take that negative down here, then I do get 5, 1, negative 2, 1. It's kind of neat. This process of finding inverses for 2 by 2 actually directly relates to finding the inverse for a rational function. The coefficients just switch, just like they would in a 2 by 2 matrix. That's crazy. You don't have to do that, but it's interesting to know that it's there if you want to use it. So, what I was saying earlier about this whole process. If I had one equation, if I had this here, and I just solve for x, I wouldn't do anything special. I would just solve for x, right? If I had a billion equations where I knew z, but I didn't know x, it would be a good idea to first solve for x, right? This is a really good equation for if I know x. You understand what I'm saying? This is a really, if I know x, z's already solved for, yay. But if I have a billion equations and I have to solve for x each time, I'd rather just solve for x once. So I'd multiply by 10, add 7, right? That's just finding the inverse in a way. How we know so far? So when I'm given this, when I have an equation like this, I could just do it the way we did before. I could just draw this augmented matrix, number, where that would be the answers, right? And this would be my coefficients. We could just solve it like that. That's sort of like doing this. Or I could find the inverse of A and apply that to the other side, so like we did here. So if I have, so there's no need to find A inverse. If I just have one system of equations that I have to solve and it's never going to happen again, I'm just going to attack it directly like we did before. I'm going to augment the matrix with the answers and just row reduce it. But if I had a bunch of these, I'd rather have x solved for,
AB.
and then I could plug in what the b is for a situation and figure out what x is, right? This is really good for if I already know what a and x are. Normally I don't. So I can solve for x directly, right? Especially if I have a whole bunch of these. So I don't know if that... So here, this is good if I just have to do it once. I would solve for x if I had to do it a billion times. If it was a computer program, that would add up to a large time savings. Right? Same idea with what we just did. We solved equations like this before. Totally, it's what the handout had. It's solved in an equation. But now we have a different way to do it, and this other way to do it is very useful if I have a whole bunch of equations like this to solve with the same coefficients. Then I just have to be given the different answers. Negative 2, 0, 3. Maybe now it's 1, 7, 8. I would just do that. 4, 8, 10. I would just do that over and over and over again. Whereas up here, if somebody kept telling me z is now 1, I've got to solve for x. Z is now 2, I've got to solve for x. Shit. Let me just solve for freaking x first, and then plug my z's in every time you give me a new z. So that's the relationship between what we've done before and what this represents. Okay. So you do have to memorize this little, this here, for 2 by 2 matrices. And of course the process for finding it for larger matrices, for 3 by 3. You have to know how to find an inverse for that. This little AD minus BC piece, when would this freak out? When AD equals BC, right? When it equals 0. So that would mean that there would be no inverse for that. So whenever AD minus BC is 0,
There's no inverse.
there's no inverse. So somebody remind me, what was that? Yeah.
So is that talking about the original A that we're checking on that one? Is that checked for?
Which check? Where?
Where you were just talking about the AD minus BC.
Yes.
So that's not A inverse. It's just A equals.
Yes. So that was my AD minus BC. We got a 7, so that meant that it exists. The inverse exists. If AD minus BC was 0, then my inverse would be somehow infinity. That's no good. So I can't find the inverse if this guy, which we call the determinant, if this guy is 0, we can't find the inverse. For a 2 by 2, finding the determinant is easy. For a 3 by 3, it ain't as easy. It's very freaky. And that's from the section we're not even going to cover. So look back real quick. Remember those two matrices I gave you that multiply to be 0? Let me see if I got it here. So either one of them doesn't matter. What's the determinant of this guy here? What's AD minus BC? 12 minus 12. Right, not 0 is factor. 0. Right, and for the other guys, the same thing. So it's not every one of these is a 0 divisor, but in order to be a 0 divisor, this must be true. It's very interesting. In order to be a matrix that you can multiply some other matrix by to get 0, that actually has to be true, which makes sense. Think about it. So you're like trying to divide by 0 if you want to find the inverse, and that's why if this is 0, you can't find the inverse. It would require you to divide by 0. That's why I call them 0 divisors. Okay. Freaky stuff. Alright. Cool. So, how do you guys feel about that? Yeah.
I was just going to say, so when the determinant is 0, then there isn't an inverse for
You-
any size.
For any size. And finding the determinant for like a 3 by 3. If I had a 3 by 3 and I wanted to find the determinant, I won't get totally into this, but just a little. What you actually end up doing is you end up picking like a row, and then you take these little off row 2 by 2s and you find this guy's determinant. And then you go here and you take these two and you find this determinant. You have to actually piece it together from 3 smaller determinants. So you can imagine if I go to a 4 by 4, I got to break it down into little 3 by 3s, and I got to break each one of those down into little 2 by 2s. Holy crap! So the process of finding determinant actually does equal like how big your matrix gets. It keeps getting harder and harder and longer. You know, the bigger your matrix gets. So determinants are not fun. Thankfully, the calculator just eats that up. Bless you. So I'm not going to make you do determinants. If you look at section 10.6, we don't even do it, but that's really what it's all about is determinants.
Are we talking about memory?
This is all 10.5, yeah. So one more example of this, and then I want to get to some other stuff. Let's see. So here, let me make sure we see it. So a good first step would be to write it as AX equals B. It's not currently really in that form.
This is your answer, right?
Yep. So B is 11, negative 4. We know how to make matrix A since we started talking about matrices. What does matrix A do with this? It just collects all the what? Coefficients. So we sometimes call it, remarkably enough, the coefficient matrix. You're really, really creative. So A is just the coefficients. To make these equations happen, what do I have to multiply that by? XY. Bam. So there's A. So what it's always been, the collection of the coefficients times the variables would actually give you these equations, and they have to be equal to the given answers. So there's that system of equations written in AX equals B form. So now if you take a minute and find this guy's inverse, you could just apply that to the other side.
Would you want to take the determinant and multiply it at the end, or would you want to
Yeah.
multiply it?
That's totally up to you. I would probably multiply at the end,
Yeah.
right? You can have this piece, in fact, the definition has it sitting outside, doesn't it?
Yeah.
Kicks ass. So then you can multiply matrices together and do that at the end. So you don't have all these fractions running all over the place. So this is what you should be getting for your inverse. So the really good question up here was, do you have to bring that 1/2 in? Hell no. In fact, the form of it has it outside. You can see how it's useful. I don't want to deal with fractions in the middle of my work. I bring them in at the end. So then if I do this to both sides, on the same side, of course, if I did it on the other side, I wouldn't be able to do a damn thing anyway. Should be able to catch that pretty quick. So this is equivalent to doing AX equals B and multiplying both sides by A inverse. So here those should cancel. Let's verify that real quick. So I get here, I get 1/2, 12 minus 10 is 2, 6 minus 6 is 0, negative 20 plus 20 is 0, negative 10 plus 12 is 2, sure enough 1/2 of 2, that makes it 0, 0, 1, 1. So that's going to be the identity matrix times this. So that effectively cancels. So I just get x, y left. It's just a verification step, right? And then over here I just have to multiply these out. What do I get?
30
33
plus 8.
plus 8,
41.
41. And then negative 55 minus 16.
So that's something. There's 71.
So then the answer is, we've got it.
41 over 2 is 7. Negative 7 over 2.
Yeah, exactly. Okay. 41 over 2, negative 71 over 2. Bam. Just throw those fractions in at the end. You don't have to worry about them then. You're done. All right, maybe. It's the exact same thing for a 3 by 3. It's just a little longer, right? Just the process is a little bit longer. Okay.
And then that in the 3 by 3, we're not using a determinant.
Yeah, it's built in. So this is just a shortcut. Because the 2 by 2's determinant is very easy to represent in general. The 3 by 3's is not easy at all to represent in general. So we don't even try. We just say, it's no shortcut, do the whole damn thing. But this is what you would get if you did the little Memorex dude, put the 1001 and did it, you would get this. It's just a shortcut then, that's all it is. Cool. 3 by 3, too bad, no shortcut. Alright. So that's all section 10.5. We don't do section 10.6. Let me give you guys an example. Oh, there. Keep that up there for a little bit. Take a second and help me out with this. Can you guys add that?
Not yet.
Well, I mean, can you do what you need to do so you can add that?
Yes.
Yeah, good, do it.
X plus 7.
It's not too bad, right? Just one of them needs something, right? He needs
2x plus 1.
he needs another 2x plus 1. Of course, be careful, you can't square top and bottom of a fraction, right? But you can multiply by something. So sure enough, you get 8x plus 4 plus 3 is 8x plus 7 over 2x plus 1 squared. I like to start with this example because this is the one that students understand the least. Why we need to do what we do. But you notice how this could not exist unless I had both of these pieces, right? Can I reduce either one of these in any way? No. So they are both distinct things that have to be in this sum in order for this answer to exist. Very strange, long way to say, there it is. Right? But they have to both be there. So what we're going to do is we're going to say, okay, tell me we don't know this. We have to figure out where this came from. Right? And it sounds horrible. I love that, right? But what you do is you know what the answer has to look like. If the bottom is some repeated factor of linear something or other, it must have come from a number over 2x plus 1 plus a number over 2x plus 1 squared. So if it was cubed, I would just have another entry here, right? So, in fact, we know this came from a number over 2x plus 1 plus a number over 2x plus 1. We know it did. But in general, whatever this is would have had to have come from this. In fact, students will say, why do you need that piece? Well, because there's no way a number could equal 8x plus 7. You have to have this piece there for this to exist. Yes, sir?
Why couldn't the A have underneath it a squared as well? Like, how would you know that?
No, because then what you really would have is you'd have a times 2x plus 1. there has to be a situation, there has to be, you have to allow for, yeah, exactly. If you do the math, A might come out to be 0, and the math is telling you, you really didn't need that. Okay, maybe. So watch, I want to start with this guy, because we know what the answer is. I know that A is 4, and B is 3, right? So how in the world would I solve this? This is kind of cool. There's a whole range of mathematics in which, to solve it, you guess at what the answer looks like, and then start messing with that. So my true variable in here, in a way, is not x. My true variables are A and B. Right? And they're parameters, really. Not really variables, but they're parameters. How do I make this happen? So what I can do now is, of course, if I'm trying to solve this equation, what's the worst part about it? All the crap on the bottom, right? How do you kill the bottoms? Multiply by 2x plus 1 squared. Multiply by the LCD. So that's going to kill that. On this side, it's going to kill that. And what happens here, of course? One of them dies and he picks up another one. So then I get this. I get 8x plus 7 equals
2x.
So I get, now here's the really cool part. 8x plus 7 has to equal 2ax, cool, plus a plus b. So what must 2a equal in order for this to make any damn sense? 2a has to equal 8. Can you guys see that? Again, the creative geniuses who are mathematicians, we call this equating coefficients. The coefficient of x over here has to be the same as the coefficient of over there, or there's no way it's going to work. So 2a has to be 8. So what's a? 4. That's craziness, right? So we already knew that. And what's a plus b got to be?
7.
Yeah, those are the constants, right? There's no variables on them. Those are the constants. So I know a is 4, so what's b got to be? 3. Kick ass. Alright, so I want you to buy into this idea. Sounds like it's going to be remarkably difficult to break this back up. But it isn't. That's not that hard. It's not always think it's easy.
No.
It's a little bit harder. Alright. Let's try one more, and then I got a little handout for you that summarizes everything that could possibly happen to you. So let's say I had this here. So one advantage we had here is the bottom was already factored. Right? Pretty, I like the way. Right? So how do you prettify the bottom here?
Factor it.
Factor, cool. So what do you get there?
X plus.
No, it's
Here.
1 plus 1.
Yeah, this is one of the evil ones. It could be 6 or 1, or it could be 2 and 3. This guy's got to be 2 and 3. Small ass numbers, but it's one of the weirdest little freaky factoring dudes there is. So what's this? What should this have come from then? Can you guys see where this should have come from? This would have come from what? Why did we factor this? Yeah, it should have come from some number over x minus 2 plus some other number over x minus 3. Now, a and b might end up being equal, but as far as I know, they have to allow for them to be two separate numbers, right? So it seems to me the heart of this is factor this bad boy. Put a over a piece plus b over a piece plus c over a piece. And if there's anything that's squared, if this would have been squared, I would have had to have one more piece that's over that square. Same way over here. So if there's a repeated piece, you have to repeat it in your possible answer for every possible power. This is all explained on the little handout too. So now the next step, once I got it set up, what's the next step? Yeah, multiply by the LCD. Now hopefully you guys see, he's just going to pick up the other dude. And he's going to pick up this dude. Is that okay? If I multiply it by the LCD, that's what's going to happen. Now let me show you a slightly different way to do it than what we did here. This way it'll always work. This way of equating coefficients. I could distribute the A, distribute the B, get my X stuff together, get my numbers together, so forth. But let me give you one other method, and I show this on the handout too. What makes this... What sucks here is I got A and B. I got two things I'm trying to solve for. So how would you kill this piece? You can control X, because what can X be? X could be anything. And specifically, if I make X 3, this will go away. So if X is 3, this will be 0.
Yeah.
What do I get here?
5.
5 equals 0 plus
1. B.
B times 1. So B. So B is 5. Kick ass. So if X is... What's the other one? 2. If X is 2, I'll get 2 equals 2 minus 3. Negative A plus 0. Right? I made that one die. So again, once I write this, X could be any damn thing I want it to be, and this should still be true. That's when I set that equation up, that's what it's saying. So if X specifically is 3, this equality is still true, and that value makes A go the hell away, so I can get B by itself. Do the same thing for B. Make X 2. Make B go the hell away, and get A by itself. So what's this actually become? 3x minus 4 over this came from... Where'd it go? A is negative 2 here, right? So it came from negative 2 over x minus 2 plus 5 over x minus 3. So I've broken that down. It's called partial fraction decomposition. Decomposing it. So let me give you this handout. It's got everything on it that we just did, plus some more.
1.
This is 10-7.
Oh, it's just 10-6, okay.
This is really, really useful in calculus. If you're not going to calculus, then this is really useful for the questions I'm going to ask you now.
Next question.